All right, continuing, the next objective in Chapter 11, Section 1 is to look for a pattern in a sequence and try to determine the general term. So remember, the general term is we're looking for a function or a rule that we can use to represent that sequence. So write the general term of the sequence. So we have our list is 2, 4, 6, 8, ... and we are looking to write down a rule that represents this. So the first thing we want to do is look for a pattern. So what is happening each time as we move to the next term? So what happens when we go from 2 to 4, and what happens when we go from 4 to 6? Well, each time we are adding the same number 2. So we have to be a little bit careful because we might erroneously think that the rule is a sub n equals n plus 2 because we're adding 2 every single time. But that's not the case. So if we check this by putting in some different values, so if we tried a sub 1, we would get 1 plus 2, which is 3. A sub 2 would be 2 plus 2, which is 4. And a sub 3 would be 3 plus 2, which is 5. This does not generate the correct sequence. So the key idea that we need is the following. So if we were to ask the question, well, what's 3 times 2? Well, we would all say 6. But the real question is, well, why is 3 times 2 equal to 6? Well, this tells us that we are going to add the number 2 to itself 3 times. So 2 plus 2 plus 2 is 6. So the key idea is repeated addition is multiplication. So if that's the case, if we're repeatedly adding the number 2, what we really have is a sub n is equal to 2 times n, or 2n. And now if we check, well, a sub 1 is 2 times 1, which is 2. A sub 2 is 2 times 2, which is 4. And a sub 3 would be 2 times 3, which would be 6. All right, let's take a look at our next example. So if we look at B, we now have the pattern 4, 7, 10, 13, and so forth. So what are we adding each time? Well, to get to the next term, we're adding 3 each time. So based on what we just talked about above, we would say then b sub n should be 3 times n. But if we check our first few terms again, we would have 3 times 1, which is 3. We would have 3 times 2, which would be 6. And our third term would be 3 times 3, which would be 9. So these are not quite right. In fact, every single one of these terms is too small by the amount of 1. So if I were to add 1 to each of them, it would give me the proper values. So that means my actual general term of the sequence would be b sub n equals 3 to the n, which gives me the proper skip. I'm adding 3 each time. But then I was off sequence by 1, so I had to correct that by adding 1 to get to that number. And we'll note that we have what our skip was 3, which was the number we had right here. And what did we have to do to that to get to 4? Well, 3 plus 1 gave us 4, so we knew we needed the plus 1. The next example is for you guys, so go ahead and try this one. So our sequence this time is the numbers 2, 7, 12, 17, and so forth. So the skip this time is we're adding 5 each time to get to the next sequence member. So we're going to start with C sub n is equal to 5 times n, but we don't want to start at 5. In fact, we want to start at 2. So what do I have to do to the number 5 to get to 2? Well, 5 take away 3 gives me 2. So my general term of this sequence is going to be 5n minus 3. All right, let's take a look at our next example. So we have the sequence 3, 9, 27, 81, 243, dot, dot, dot. And this time, if I try to add, I notice that 3 plus 6 gives me 9, but 9 plus 6 doesn't give me 27. So we're not adding the same thing every single time. But what are we doing? Well, I notice that 3 times 3 gives me 9, and 9 times 3 gives me 27, and 27 times 3 gives me 81, and 81 times 3 would give me 243. So instead of adding the same thing every time, I'm multiplying by the same thing every time. So now that begs the question, if repeated addition is multiplication, what is repeated multiplication? Well, the key idea here is that repeated multiplication is an exponent. So if our repeated multiplication is an exponent, we're going to have d sub n is equal to our base, well, we're multiplying by 3, and then our exponent is n. And if we check that, 3 to the first power is 3. 3 squared would give us 9. 3 cubed is 27. So that does indeed generate the sequence. All right, so let's take a look at our next example. So this time, when we look at it, we try to see if we're adding the same thing every time, but that doesn't appear to be the case. And if we try multiplying, well, 1 times the square root of 2 is the square root of 2, but the square root of 2 times the square root of 2 gives us 2, but the next term is supposed to be the square root of 3. So if we're not adding the same thing and we're not multiplying by the same thing every single time, a strategy that might be helpful is to write the sequence as an input-output table. So if we do that, if we write it as a table, I'm going to have my n's, and then I'm going to have my e sub n's. So we know that the inputs are always the natural numbers, so 1's going to get paired with the first element of the sequence, which is, or the first sequence member, which is the first one in the list. Our second one, 2, is going to get paired with the second one, which is the square root of 2. And then our third term is going to be the square root of 3. So 3 gets paired with the square root of 3. And finally, the fourth term, 4 gets paired with 2. So now we look for a pattern in the table. So 1 gets paired with 1, 2 gets paired with the square root of 2, 3 gets paired with the square root of 3, and 4 gets paired with 2. Well, this seems to imply that our rule is we take our input n and we're taking its square root, because the square root of 1 is 1, Square root of 2 is the square root of 2. The square root of 3 gives us square root of 3, and the square root of 4 gives us 2. So the next member of the sequence would be the square root of 5. All right, so let's take a look at our next sequence member. So this one, we have 3, 1, 4, 1, 5, 9. And once again, if we look for addition, if we try to add the same thing every single time, that doesn't work. And if we try to multiply by the same thing every time, that also doesn't work. So we could try to make a table, but this sequence, we can't actually write down a very nice general term. So f sub n is the nth digit of pi. So we know pi is 3.141592, blah, 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 and forever. And so this is a well-defined sequence, but there's no rule that we can write down that will generate all of the digits of pi. All right, let's take a look at our next sequence member, or our next sequence. So in G, we have the sequence 1/3, 3/5, 5/7, 7/9. When we have something like this, oftentimes it's good to analyze the numerator and denominator separately. So to go from 1 to 3, I'm adding 2. To go from 3 to 5, I'm adding 2. And to go from 5 to 7, I'm also adding 2. Similarly, in the denominator, I'm doing the same thing. I go from 3 to 5 by adding 2. I go from 5 to 7 by adding 2. And from 7 to 9 by adding 2. So now if I want to write G sub n, I'm going to analyze each of these. So repeatedly adding 2 means we're going to have 2 times n, but then I want to start at 1. So to get to 1 from 2, I have to subtract 1. Similarly, in the denominator, I'm adding 2 every time, so I have 2 times n, but the first term in the denominator is 3. So I add 1 to 2 to get to 3, so that gives me 2n plus 1. So then the general term of this sequence is going to be 2 to the n minus 1 over 2 to the n plus 1. So next one is for you. So go ahead and try to find the general term of this sequence. So this time we have 2, 4, 8, 16 in the numerator, and 5, 10, 15, 20 in the denominator. So in the numerator, each time to get to the next term, I multiply by 2, I multiply by 2, and I multiply by 2. And in the denominator, to get to the next term, I'm adding 5, I'm adding 5. So then my h sub n is going to equal, well, multiplying by 2, multiplying by 2, multiplying by 2. So I'm going to have 2 to the n in the numerator, and then adding 5 every time is 5 times n. So h sub n is 2 to the n divided by 5 times